Hello again. Hope to see you one day live. Maybe with Leah, we can organize a meeting once everything is over. Now we'll continue with our specific immunity and enter the chapter 1, T lymphocytes. We will talk about the selection of lymphocyte, the role of lymphocyte, differentiation of lymphocyte, and what kind of lymphocyte do we have. And then we will move to the final chapter next time with the B lymphocyte. Everything starts in the thymus. Of course, B cells are born in the bone marrow, but differentiated in the thymus. Medullary T cells or prothymocyte colonize the thymus. The thymus is a lymphoepithelial organ made up of two lobes separated by septum and surrounded by a capsule. Each thymic lobe is divided into lobules by connective tissue. Irrigation is provided by vessels from the thoracic arteries. Here is the thymus, two lobes, left and right, and if you make a section, transverse section, you can see that we have, like we mentioned earlier, we have a cortical part and then peripheral part and then central part, and we will see the role of each part of the thymus. Each lobule has two zones, a peripheral zone and the cortex, and the populated with cortical thymocyte, which are produced by the multiplication of prothymocyte coming from the bone marrow. So the cortex is populated by a very high number of cortical thymocytes. A medullary zone, which is central, contains in lower density mature and differentiated T lymphocytes. So in the thymus, the cortical part, a high number of prothymocyte, and in the medullary, low number of differentiated and mature lymphocytes. Epithelial cells, dendritic cells, and macrophages are also found in both in the cortical as well as in the medulla. So the thymus is like a school, which has teachers, and also we have logistics to feed the student. The epithelial cells are here to feed the student, produce thymic hormones, which influence the maturation of the thymocyte. Don't keep in mind that the prothymocyte is just baby lymphocyte, immature, they will maturate, be selected, and then they will leave the thymus. The epithelial cells are playing the logistic part, while dendritic cells and macrophages are playing a role of instructors or teachers. Dendritic cells and macrophages are antigen-presenting cells and therefore express major histocompatibility complex, class 1 and class 2. Always, this immune system is teaching us, instead to hire two teachers speaking two languages, we will hire one teacher speaking two languages. Here we have dendritic cells and macrophages. In one hand, there are nucleated cells expressing MHC class 1. In the other hand, there are professional cells expressing MHC class 2. So basically, one cell, dendritic and macrophage, are expressing two kinds of MHC molecules. By migrating from the cortex to the medullary zone, the cortical thymocyte gradually differentiate, expressing at each stage surface protein cluster of differentiation, what we call CD, CD4, CD8, and CD3, and so on. We will see what kind of CD we will find in each step and for each level of maturation. The cortical thymocyte expresses CD1, CD4, CD8, triple positive. The medullary thymocyte no longer expresses CD1, gone, and it's replaced by CD3. So all maturated lymphocytes are CD3 positive, but there are either CD3, CD4, or CD3, CD8. You can never find CD3, CD4, CD8. No, CD3, CD4, CD3, CD8. So basically, all T cells are CD3 positive. CD4 cells are CD3, CD4 positive. CD8 cells RCD3, thymic selection. Since TCR receptors are produced randomly from genetic recombination, there is a risk that some of them will recognize the antigen of the cells are foreign. Would result in the self-destruction of the individual. So we don't want to have cells that can make the irreversible mistake, inducing autoimmune. The thymocytes carrying such receptors must therefore be eliminated. There is a selection of lymphocytes. I don't know. Thymic selection. Since TCR receptors are produced randomly from genetic recombinations, there is a risk that some of them will recognize the antigen, self-antigen as foreign. Such recognition would result in the self-destruction of the individual cells by its own immune system. The thymocyte carrying such receptors must therefore be eliminated. This is the selection of lymphocytes. We will see how this selection occurs and when. The TCR of T lymphocyte must simultaneously recognize an epitope associated with an MHC class 1 or 2 molecule. The selection of lymphocytes is therefore done in two stages, positive one and the negative one. Positive selection. It is happening in the peripheral, where you have all the pro-thymocyte, and they will be asked the following question. A positive selection in the cortex, which select the cortical thymocyte, capable of recognizing the MHC. They will be asked, are you capable to recognize MHC molecules? Just. Thymus cells carry MHC, class 1 and 2. We know that. If the TCR, this baby thymocyte, through the TCR, does not recognize MHC molecule, he can face it, but doesn't know what is it. It is eliminated by apoptosis. If the TCR recognizes a MHC molecule, it will be preserved. Now, it will be differentiated based on the MHC it has recognized, MHC class 1 or class 2. Lymphocyte selection is impressive. Only 5% of the thymocyte are retained. 95% coming from the pro-thymocyte, coming from the bone marrow, will be eliminated just because they couldn't answer the question, are you capable of recognizing MHC molecules? The one they have recognized, they belong to the 5%. The one they have recognized, the MHC class 1, they will become CD8 positive. And the one they have recognized MHC class 2, they will become CD4 positive. Here, where the differentiation will start, where the CD8 and CD4 are born. They are born in the cortex by recognizing the MHC class 1, MHC class 2, and they are among the happiest 5% they make it through. Is it done? No. They will be asked the second question. Are you capable of recognizing the epitope, the antigen, on those MHC class molecules? They retain lymphocyte and they migrate to the medulla. That's why we said lower density, negative selection. The 5% will be exposed to this. A negative selection in the medulla, which eliminates by apoptosis the thymocyte recognizing the self-antigen. We said in the scenario number 3, normally a T cell cannot attack self-antigen. And it starts here. All the cells that will recognize self-antigen as foreign antigen will be killed. Why our structures, teachers, macrophages, dendritic cells are presenting self-antigen. Why they are not presenting non-antigen and make story easier? It is not possible. Nobody, no organism can predict what tomorrow will be on terms of antigen. That's why we will just present self-antigen, and T cells will deduct, will make conclusion, and of course recognize foreign antigen because they know only self-antigen. It's not possible to put all foreign antigen in anybody because it is so huge and of course unpredictable. Before 2019, before December 2019, 1 year ago, we have never heard about coronavirus. It is a foreign antigen. That's why we can always learn that they are coming, and we know our self-antigen, and of course we will deduct and make decision about foreign antigen. If the TCR recognizes MHC plus self, here recognizes, which means stop, it will be eliminated. A T cell never stop when it is from facing self-antigen. If the TCR does not recognize the MHC class 2, which means does not stop, it will be preserved. And here, from the 5% luckiest one, we have also maybe 50% gone, which means from the bone marrow to the medulla, we have about 2 to 3% only of immune competent cells, they make it through. And here, in the cortex, our prothymocytes are CD3, CD4, CD8 negative, and then they will, of course, be CD3, CD4, as you see here, and then it will be either CD3 and CD4 or CD3 and CD8. See, you see, never you can find mature cells with CD4, CD8. No, CD3, yes, all the cells are CD3, but they will be either CD3, CD4 positive or CD3, CD8 positive, but never double positive for immune professional or mature differentiated T cells. The preserved lymphocytes are immunocompetent lymphocytes. They can leave the thymus to colonize the peripheral lymphoid organs. They can go to lymph node, they can go to the spleen, they can go to the tonsils, and they can go to the Peyer's patches. The thymus does not have lymphatic circulation, so that T cell they have come out will never return to the thymus. One way, you are either professional or you are not. The thymus undergoes from puberty a very progressive evolution, but never disappear completely. So the thymus, we believe that maybe it can continue to produce some T cells, but never in this quantity and the quality that before puberty. That's why we said upfront for every single entry of antigen, what we have one cell out of 100,000 mobilized, and the rest will be, of course, this deficit in number will be compensated by cloning of these cells in order to reach the number to produce either cytokine or to attack foreign infected cells. And here, what do we have here? We have stem cells, double negative CD8, CD4 cells, and then double positive CD4 that are immature, and then they will go. The first question is positive selection. Positive selection is, are you capable of recognizing the MHC? MHC class 2, CD4 is born. You recognize MHC class 1, CD8 is born. The one they cannot recognize, they will of course die through apoptosis. Here, 95% of the cells are already killed. 5% will make it through. The second one is, are you capable of recognizing that we are presenting to you only self-antigen? The one they will stop, which they should not, they will be killed, negative selection, and then maybe just 50% will make it through. A huge selection in order to produce only immunocompetent lymphocytes. The physiological significance of presentation of antigen. It is expected that this precision in the regulation of the degradation system of the protein antigen and their presentation plays an important role in the stimulation of the immune response. The benefit of restricting T cell receptor to MHC-associated peptide allows T cells to recognize and respond only to cell-associated antigen. MHC only load peptide inside the cells where antigen of the phagocyte intracellular pathogen are present. So only there is this association between or collaboration between antigen-presenting cells and T cells through the MHC that are bringing the peptide and presenting to lymphocytes. By differentiating between MHC class 1 and 2 in antigen presentation, the immune system responds to intracellular and extracellular microbes in the best way to combat these microbes. MHC and CD4, CD8. Here we have MHC class 2. We have macrophages capturing the extracellular microbe presenting to CD4 through MHC class 2. This CD4 is called CD helper cell, will secrete cytokine. Cytokine, they will activate macrophages in order to phagocyte and, of course, be a better killer. B cell is also antigen-presenting cells, since it can recognize extracellular microbe, phagocyte and present. Now, this CD4 helper cell will help this B cell to produce better antibodies. That's what we will see in the next course, what we call class switching. So these helper cells, as you see here, are helping either the macrophages to phagocyte more and destroy more germs, or helping B cells to produce better antibodies. CD8, MHC class 1, infected cell. This cell knows that it will die. It's rather presented to CD8 in order to die through apoptotic pathway, which is programmed cell death, clean, and then taken with it the virus. If the CD8 cells will not make it first, this virus will multiply and kill infected cells, and of course it will spread. So CD8 cells is always in front of MHC class 1, killing of antigen expressing infected cell. Antigen presenting cells, bilingual, capture the germ. In one hand, presenting MHC class 2 to CD8, CD4. CD4 will secrete interleukin-2 in order to activate, I said earlier, one cell out of 100. So to compensate this deficiency number, it will clone itself, clone it. And then here we will have CD4 cell that will activate macrophages, B cells, and other cells, and we will have memory CD4 cells. CD8 cells, the same story, presented through MHC class 1, secreting interleukin-2, cloning, and then we will have effector CD8 cells killing affected target cells, and of course, activating macrophages, and of course, we have memory. That's why sometimes with coronavirus, we talk about this cross immunization, which means we can have some memory of other corona through these memory T cells that can help us fighting through this COVID-19. Function of class 2, the whole is recognized by the helper T lymphocyte as part of no cell, which causes the activation of the onset of the immune reaction. Differentiation now, these CD4 cells, CD8 cells, it's clear they will attack and kill infected cells. CD4 cells, we have heard about type 1, type 2, TH17, and so on. We will see now about how many subclasses. CD4 cells can differentiate into two classes which will produce different cytokine, which will play different roles. The two classes are TH1 and TH2, T helper 1 and T helper 2. CD4 TH1. Cytokine produced by TH1 are interferon gamma, the most important. Interferon gamma activate macrophages and B cells for the production of antibodies, which allow phagocytosis of microbes. So based on the cytokine, we know what kind of subclasses of CD4 cells we have. If we have interferon gamma, then we have Th1. Macrophages and dendritic cells also respond to bacteria and viruses by producing the cytokine interleukin-12. When T cells recognize the antigen from these microbes that is presented by these cells, they become exposed to interleukin-12. So the macrophage is not just any cell just taking away germs. No, the macrophage is capturing, of course, phagocytosis, but also secreting interleukin-12 in order to help T helper cells to switch to Th1. So these cells will be exposed to interleukin-12. Interleukin-12 will allow the differentiation of T cells into Th1, which will produce interferon gamma. Communication, positive communication. Interferon gamma will activate macrophage to kill microbes. So, summary, macrophage capture, phagocyte, express, present, but also secrete interleukin-12. Th0 effront will receive the antigen and the interleukin-12. By being exposed to interleukin-12, it will become Th1 secreted interferon gamma. Interferon gamma will be secreted to the macrophage, and the macrophage will be activated and kill more microbes. CD4, Th2, T helper 2. T helper 2 cells produce interleukin-4, which stimulate the production of IgE, and interleukin-5, which activate eosinophils. We can find that, of course, in anti-parasite reaction, but also, unfortunately, in allergic reaction and some asthma. Th2 cells activate the response against parasites such as helminths. When the infectious agent, will not allow the secretion of interleukin-12, so the macrophage will capture the parasite, but it will not secrete interleukin-12. And the T cells, by not receiving interleukin-12, it will become Th2. And Th2 will, of course, will allow the cell to secrete interleukin-4 and interleukin-5. We will see it here. Here we have antigen-presenting cell, capturing, for example, a virus. It will present it to CD4 naive. CD4 naive will secrete interleukin-2 in order to clone, and then the macrophage will secrete interleukin-12. This T cell naive will become Th1, but because it has been exposed to interleukin-12. Now, if in this case we have parasite, there is exposure, there is cloned, but there is no secretion of interleukin-12, some other sources, such as basophil can secrete interleukin-4. Receiving interleukin-4, the cell tells the T naive cell will become Th2, and then will secrete in its turn interleukin-4, interleukin-5. Here Th1 and here Th2. Th1, viruses, bacteria, there is capture, presentation, secretion of interleukin-12. Interleukin-12 will help naive CD4 cells to become Th1. It will secrete interferon gamma, which will help the macrophage and activate macrophage to kill more microbes. And interferon gamma will help B cell to, of course, to secrete IgGs, what we do need in case of infection and some bacterial infection. Now, if you have a parasite, there is a capture, there is presentation, but there is no production of interleukin-12. The T naive cell will become Th2. It will secrete interleukin-4. Interleukin-4 will help B cell to switch and produce IgE, much needed in case of parasite infection. And of course, secrete interleukin-5, recruit eosinophils, also needed cells in terms of parasite infection. But unfortunately, this case can also be seen when we have allergic reaction. Even if we don't have a parasite, we have some allergens that can also trigger Th2 reaction, IL4 and IL5, and maybe one day we will make just a special conference on terms of this reaction, what we call wrong reaction front of non-harmful antigens such as pollen or some dust or some small insect, but unfortunately they can trigger the same reaction and they can harm the body. Now we have cellular immune response and then humoral immune response. When we say cellular, usually T cell. When we say humoral, it's antibodies. Antigen presenting cells capturing through one hand CMH class 2, communicating with T helper cells, Th0, secrete interleukin 2, and then clone itself. And by receiving interleukin 4, it becomes Th2. Th2 will help B cells, of course, to produce antibodies. And by receiving interferon gamma, we can, of course, produce, for example, IgGs. Now, if the cell has received interleukin 12, this you see here, CD4 cells will become Th1 because it has received, and then Th1 will, of course, help producing, either inducing the cellular immune response and secreting, as you see here, interferon gamma in order to help B cell to produce, as I said, IgGs. Now, with CMS class 2, will present to CD8 cells. CD8 cells, of course, will multiply, clone itself, and then we have effector T cells, either memory cells or, of course, killer cells. There is always communication, and there are always cytokines going from either the Th1 or, of course, Th2 in order to help to produce the best antibodies and the required antibodies. Now, what do we have on this CD4 naive cells? Everything starts with the presentation of the antigen and, of course, the secretion. If the naive CD4 cell will receive interleukin 12, it will become Th1. Th1 secretes interferon gamma mainly, promotes tumor immunity, intracellular pathogen, and drives to autoimmunity. If now it doesn't receive interleukin 12 rather than interleukin 4, it will become Th2, and then it secretes interleukin 4, 5, 13, extracellular pathogen, allergies, and asthma. Now, if it receives also interleukin 21, it will become Th17 by secreting interleukin 17A, F, interleukin 22, interleukin 21. It is controversial on terms of tumor immunity, breaks immune tolerance, extracellular bacteria play a role in autoimmunity, and some of them will be also T regulatory cells, secreting TGF-beta, interleukin 10, 20, 35, suppression tumor immunity, promote immune tolerance, maintain lymphocyte homeostasis. So we do have at least 4 known TH subclasses: Th1, Th2, Th17, and T regulatory. And of course, it starts here. Just another slide. Dendritic cells communicated with naive CD4 cells. We have, of course, Th1, interferon gamma, Th2, interleukin 4, 5, 13. T follicular cells, we will see them in the follicular, the lymph node and the spleen. Th17 secreting interleukin 17A and F, and T regulatory secreting. But based on the secretion of cytokine, we can deduct, we can know if we will find in our cytokine reader in the serum interferon gamma, we know that we have Th1. We will find interleukin 413, we have Th2. If we find interleukin 21, we have T follicular cells. If we will find interleukin 17, we have interleukin Th17 and so on. Every single subclass of these T helper cells has its own production, and here we have this T follicular that they will help B cells to do the class switching. We'll find them in the cortical part where we have the B cells residing, and B cells will communicate with T cells always with these follicular cells through this CD40 ligand receptor. So without this communication, the B cell cannot switch. It will continue to produce IgM. But with this communication, it will switch to IgG producing cell, IgA producing cell, or IgE producing cell. So there is a huge communication between B and T, and then it will help us to produce the best antibodies. As we see here, so antigen presenting cells has captured, presenting to CD4 cells, and the CD4 cells will communicate with B cells, and there is production of T and the best antibodies, what we call class switching. And here what we call this positive communication or control positive, antigen presenting cells capturing, secreting interleukin 12, naive, become Th1 secrete interferon gamma to activate macrophages. So every single cell in this equation needs a communication with the other one. Macrophage communicate with T, T communicate with macrophage, and so on through these extracellular molecules, what we call cytokines. Now we have this situation of allergies. Stop. Continue. Now we have the situation with, in case of allergies, we have a pollen taken through BSU, of course, through the, when we breathe, pollen is taken by antigen presenting cells presented to CD4 cells that will become Th2. Th2, of course, will secrete interleukin 4, as you see here. Interleukin 4 will help B cells to produce IgE. IgE will bind to mastocytes. Interleukin 5 will go to the bone marrow and prime for eosinophils. Eosinophils will be there, and as long as we have IL-5, eosinophils will survive, and they will secrete their toxic product, which will harm the lungs. When you have, of course, the secondary exposure to the allergen will go directly and bind what we call cross-linking, make connection between two antibodies, and then it will provoke, induce the degradation of mastocyte, which will release. We'll have histamine, leukotriene, prostaglandin, and of course, with the eosinophils, we will have production of mucus, which can, of course, narrow, and of course, the diameter of our airways, and then we can suffocate. So basically, all the cells are communicating, sometimes in the right way, and unfortunately, sometimes in autoimmune diseases and allergies in the wrong way, and the cascade needs to be stopped. To better understand what we have seen in this course, we will see two videos. One about the escape mechanisms of bacteria. They have developed a way to escape our immune system. It is well known that all viruses and bacteria, as well as parasites, can develop mechanisms to escape. We will see three bacteria. They have very well developed mechanisms to escape our immune system. We will start with Legionella pneumophilia. As you see here in the slide, the Legionella is taken when we breathe, especially stagnant water, warm water, contained especially in the region of the Sahara, as well as air conditioning, and it enters our lungs, as you see here. It will be captured by macrophages, and here you see very well the notion of capturing phagocytosis. But what happened, the macrophages will be enabled, they lose the capacity to destroy the bacteria. They cannot. Why? Because the bacteria has developed a mechanism to avoid the formation of the phagolysosome. It will be surrounded by vesicles of the cell in order to escape the reaction of the lysosomes. It will divide inside normally, and even it will recruit ribosomes. As you see here, we have ribosomes, and it becomes now a part of the organ, of the cell. The macrophage in the lung is moving, trying, of course, to destroy it, but he cannot. while the bacteria is developing, and it will get something special, flagella, capacity to move. Now it is destroying this vesicle and ready to kill the macrophage through necrosis and get out. So it's a very powerful way. Unfortunately, the macrophage has been used as a vehicle, as a way to transport the bacteria in our system, respiratory tract, and now the bacteria is moving. The second one is Listeria monocytogen. It is well known, we can find it in cheese, for example, and we can ingest it through what we have eaten, and it enters our intestine, the system. And you see here that the bacteria is between two cells. So it will infect. Here is an infection. Earlier we have seen phagocytosis, now we see the infection. So there is an infection, and to make sure that every cell has its receptors in bacteria, you see, it's clear that we call what we call that zip-like receptors, and the bacteria is inside. Inside infected cell, the bacteria will, of course, destroy the phagocytosis or the vesicle, the vesicle, and it will multiply normally, freely, since it has infected. While developing inside the cell, other bacteria are still in the lumina between the cells and may trigger an immune response. So the bacteria inside the cells is aware that we might have some IgA, especially here, digestive system antibody, that can, of course, neutralize the bacteria if it will go out. You see now the bacteria has become mobile, taking actin from the cell, borrowing, and it knows exactly that if it will go out, maybe it will be killed by antibodies. So what it will do is to develop pseudopod, see this elongation of the membrane of the cell and enter another cell at the same time, avoiding any antibody reaction. And that's what we call escape mechanism. So these bacteria are very powerful, and that's why they can really harm and make the body in this bad situation. So the third one we will see is, of course, tuberculosis, forever young, since it can stay in our lungs for years. It is taken as Legionella. We can breathe it. The power of this bacteria is five bacteria can trigger an infection, while normally we need 1,000. So a high infective agent, and of course, very powerful mechanism. It enters our respiratory tract. It is phagocyte, taken by the macrophages normally, but exactly as earlier, the macrophages are not capable to destroy it. We believe that there is an inhibition process between the lysosome and the phagosome, and the bacteria is not destroyed. The bacteria will remain alive, it will multiply. Meanwhile, the macrophage gets frustrated and will send signals, cytokines, to recruit other macrophages or monocytes, lymphocytes, in order to destroy the bacteria. But none is capable of, and you see here, lymphocytes are coming, and they will, of course, surround the existing macrophages or macrophages that are becoming infected, and we form that what we call granuloma. Granuloma is a number of cells, macrophages, lymphocytes, monocytes, that are surrounding all the infected cells, and unfortunately, we cannot get rid of this infection. This is one of the escape mechanism we can see, and there are many, maybe in the future we can see others. The second slide or video is about capture and presentation. It's exactly what we have seen in our slides. You see here dendritic cells in the mucosa, in the intestine. Of course, here it's of course commercial, but we will take the message. When we have bacteria, the bacteria will get information from this, the dendritic cells will get information from this bacteria, either capture, antigen-presenting cells, or they get, of course, kind of wave that the bacteria will trigger in order to stimulate these dendritic cells. What we the take-home message is our dendritic cells, as you see them here with the their elongated membrane, are stimulated by different ways, and they will capture and move to our here. We don't have lymph node, rather in the intestine we have the pair patches. In the pair patches we will see both T and B cells. So our dendritic cells will move to our T cells, antigen presenting cells. Our T cells will get activated, and then they will communicate with B cells, what we call T-B cell interaction. Our B cells will synthesize IgA, and we see that IgA are the only antibody moving from the membrane and going to the lumina outside in order to stop the coming, of course, bacteria infections. You see very nice well of cooperation. Dendritic cells presenting to T cells communicating with B cells, and B cells synthesizing, of course, IgA and IgA. They will neutralize coming specific, of course, in our case, bacteria. Well, I hope these two videos did help us to understand better what we have talked, specifically antigen presentation, as was the topic, dendritic cells presenting to T cells communicating with B cells and producing, and of course, the concept of infection versus phagocytosis. Voila, we have reached the end of our second talk. Thank you very much. Hopefully, we will see you for the last one, which is the B cell and how B cells are producing antibody. Why do we need some time to see antibodies, especially now with the serology, and how our antibodies are helping our immune system to fight against, specifically against extracellular germs. Thank you very much for listening, and hope to see you again. Bye.